Hello students. So we are going to resume from where we left last time. We will be discussing about open channel flow. So I'll very quickly go over what we did last time and then we'll move on from there. All right. So the introduction to open channel flow, this we've already gone over last time, but I'll very quickly recap what we did. So the flow of fluid in a conduit with a free surface is what we call open channel flow. So this is the most fundamental definition by which we can distinguish open channel flow from pipe flow. In that, there is flow happening, but it is happening with a free surface in contrast to a closed conduit or an or a pipe flow. Okay. Now, since it is a flow with a free surface, this free surface naturally is going to be exposed to atmospheric pressure, right? And then the other significant difference between open channel flow and pipe flow is that the flow in the case of an open channel is predominantly gravity driven, right? Unlike the pressure gradient, which is what drives the flow in pipes. Okay, so if I want to give you an example of some of open channel flows, there are so many different examples. There is man-made examples that like you know spillways and canals and stormwater drains that you all see. But in addition to that, there's all so many natural examples that one can give that you've all seen seen around you. You have rivers and streams and estuaries and floodplains. All of these are instances where uh, you get to experience and see open channel flow. All right. Okay. So continuing from there. So in terms of what it would look like, I'm going to show you a longitudinal view of flow in an open channel. So if you consider, uh, so this dashed line at the bottom is what is representing the bed slope in the channel. Okay. Um, so if I assume that the flow is happening from left to right, naturally, since it's gravity driven flow, it has to flow in the direction of reducing elevation, right? So flow rate is from left to right. Then I have the water surface. Typically, we use the expression y, the letter y, to refer to the flow depth in an open channel, right? So here I have the water surface, and the distance between the water surface and the channel bed is what we refer to as the flow depth. Okay. Now, naturally, the cross section. Okay, so this is a longitudinal view. Now, if I were to be looking at this channel in this direction, right? If I'm looking at the cross-sectional view of the channel, there is so many different cross sections that are possible. Most of the times, when I have a man-made channel, I may have a defined geometrical cross section, like a trapezoidal cross section, or a rectangular cross section, or triangular, semicircular, and so on, right? So these will be defined so that obviously, since they're man-made, we would like to have a certain defined geometry for the open channel. But in the case of natural channels like rivers and streams, these cross sections may not be regular defined geometries; they may be irregular. Okay, so this is fairly straightforward. Okay, so again, we spoke about the classification of open channels. I'm very quickly going to go through this. In terms of time, you can classify them as steady flow or unsteady flow, which means that the flow parameters or the flow properties, whether it is the flow rate or the flow depth or the velocity, if they're not changing with time, then that would be classified as steady flow. If they are changing with time, then that would be categorized as unsteady flow. Now, with respect to space, you may have uniform flow, which means the flow depth or the flow rate or the velocities are not changing with space, right? Or you can call them as non-uniform or varied flow. Again, under varied flow, we have two categories. One is gradually varied flow, and the other is rapidly varied flow. We'll learn about this in the coming lectures. Which means gradually varied simply implies that whatever flow property is changing, it is not changing fast. It is changing at a gradual rate. And in the case of rapidly varied flow, it is changing quickly, right? Or it's changing within a short distance in space. Okay, so that's the most fundamental classification in terms of time and in terms of space. Then we also have the Reynolds number classification. Reynolds number, as you know, is rho vd by mu. Okay, so rho is the density, v is the representative velocity, d is the representative characteristic length, and mu is the dynamic viscosity of the fluid under consideration, right? Uh, So if I look at it from the perspective of Reynolds number, then the flow will be considered laminar if Reynolds number is less than 500, and turbulent if it is more than 12,500. Now these numbers are not exact. Okay, so it's not that if it is 501 it becomes laminar, or if it's 12,499 it's not turbulent. Okay, so these are approximate ranges. Okay, and then transitional in between these two values, 500 and 12,500, the flow is considered to be transitional. Okay, there's one more classification, which is by using what is called the Froude number. Okay, this Froude number is simply the ratio of V, which is the velocity of flow in the channel. Typically, it's the average velocity of a cross section divided by square root of gy, right? So as you know, this y, I already told you that y is the flow depth of the channel. Okay, so v is the velocity of flow. Typically, this could be the average velocity of the cross section, and y is the depth of flow. Okay, so just like if you remember, Reynolds number is a dimensionless number which gives us um, inertial forces to viscous forces, the ratio of inertial forces to viscous forces. Froude number is the ratio of inertial forces to gravitational forces. Okay, so that is how we typically classify Froude number as opposed to Reynolds number. Okay, so with the Froude number, we come up with three categories. If the Froude number is less than 1, we say that the flow is subcritical. If the Froude number is exactly equal to 1, the flow is critical. And if the Froude number is greater than 1, we call it supercritical flow. Okay, all right. So now we're going to discuss about the energy equation, of how we would write the energy equation in an open channel flow. So here I have shown over here uh, the bed slope of a channel, right? And then there's the water surface, which is flowing over the bed. And at two different cross sections located at section 1 and section 2, I have the following parameters. Z1 is the bottom elevation at cross section 1, and Z2 is the bottom elevation at cross section 2. And at these two locations, the flow depths are Y1 and Y2 respectively. So that's here Y1 and Y2. Assuming that the flow rate is steady Q, and if I know the cross-sectional details, if I know it's a trapezoidal cross-section, or if I know it's a triangular or rectangular cross-section, using this value y1, I can very easily find out v1, right? Because I know the cross-sectional details, I can find out what the velocity of that cross-section is. Similarly, if I know the cross-section details at section 2, I can find out velocity 2, right? So if I write Bernoulli equation between these 2 points, it will very simply look like this: y1 plus v1 squared by 2g plus z1, which is the total energy at cross section 1, is equal to y2 plus v2 squared by 2g plus z2 plus hf, which is whatever the friction losses that the flow is encountering in moving from point 1 to point 2. Right? As you're all aware, this friction losses, we have dealt with this for a significant portion of the semester. HF is simply F into L by D V square by 2G. If you remember, this equation was developed for circular pipes, right? So if you want to use it for non-circular conduits, right? Even in the case of pipe flow, we had developed this concept of DH. If you go back to your notes, you will find this DH, which is simply called the hydraulic diameter, which is not the diameter of the pipe, because if it's an uncircular cross section, you don't have the diameter, but you can find out an equivalent diameter, which is called the hydraulic diameter, which is represented as 4a by p, right? So that is what you would use in the case of a pipe with a non-uniform, an irregular cross section other than circular. In the case of an open channel, we use a similar expression, but instead of using this hydraulic diameter, we use one more parameter, which we call the hydraulic radius, which is simply dH by 4, the hydraulic diameter divided by 4. So it is A by P. And this R, we call it the hydraulic radius. Okay. But there's one crucial difference that we have to observe between pipe flow and open channel flow. In the case of pipe flow, the fluid is in contact with the entire perimeter of the material, right? So if the pipe is made up of cast iron or mild steel or PVC or whatever it is, the fluid inside the pipe is completely in contact with the with the ins, with the entire perimeter of the pipe, right? Whatever the pipe's cross section is. But in the case of open channel flow, one surface is exposed to the atmosphere, whatever, suppose it's a trapezoidal cross section, only the bottom and the side slopes are touching the material, whatever the material may be. It may be a concrete lined channel, it could be a wooden lined channel, it could be a brick lined channel. You should remember that this P, the perimeter, is not the entire perimeter of the cross section. You have to remove the part of the perimeter that is exposed to the atmosphere, because that is not in contact with the material. Remember, this equation is talking about friction losses, right? So this friction can only happen between the water or the fluid and the solid material with which it is in contact, right? So we are only accounting for those frictional losses. So therefore, in the case of open channel flow, this perimeter that we use the wetted perimeter. Wetted, by wetted perimeter, I mean the portion of the perimeter that is in contact with the solid surface of the bed, right? So whatever the material of the flow may be. Okay, so this is a very simple introduction to the energy equation in the case of uh, open channel flow. And remember, we will use this hydraulic radius, which is simply dH divided by 4, right? And which can be given as A by P, where P is the wetted perimeter. Okay. So now, one of the interesting things about open channel flow is that we can use what is called the uniform flow approximation to understand a variety of different situations, right? We can assume that the flow is uniform and solve a lot of practical problems, right? So now when I say uniform flow, what I mean is, as we already discussed, that the flow parameters are not changing as a function of space, right? Which means that the flow depth or the flow rate, of course, it's steady. The flow depth, the flow velocity, these are not changing as a function of space. Now, naturally, this cannot happen in a channel where the cross-section area is changing as a function of space. If I have a channel where the cross-section area is uniform and not at all changing as a function of distance, and if the bed slope is also uniform throughout the length of the channel, then you may get what we call uniform flow. And this typically happens only in long straight channels, right? It doesn't occur in winding channels and so on. So it can only happen in long straight channels where this is the important criteria. The slope is constant and the channel cross section is constant. It's not changing, right? So if it's a trapezoidal cross section at point 1, if I move to point 2, it'll be the same trapezoidal cross section with the same bottom width, with the same side slope, and so on. Right? If that happens, then we can have what we call as uniform flow. And as I said, this uniform flow approximation is very useful in estimating flow rates, right? And it's used in a so for example, if you're looking at a river or a stormwater drain or any practical situation, there's a lot of applications for using this uniform flow approximation to understand flow in open channels. Okay, so you will notice that for the rest of the semester, we'll keep coming back to uniform flow whenever we discuss open channel flow. Okay, so we'll just look at a expression, a figure for uniform flow. So let us say I have a constant bed slope, and I have 2 points along this channel, which are at a distance of L apart, capital L. Then as soon as I say uniform flow, naturally it implies that the flow depth at both cross sections is same. So if I assume that the flow rate is steady and that the cross section is uniform throughout this length, right? Then y1 is equal to y2. That is by definition, because it's uniform flow. But if the cross section is not changing and the flow rate is not changing, if y1 and y2 are the same, then naturally v1 must be equal to v2, right? So if the flow rate is steady and if the cross section area is not changing, and if, when I say uniform flow, I am implying that y1 and y2 are exactly the same. If y1 and y2 are the same, the flow rate is the same, and if the cross section details at both these locations are the same. By that I mean, if it is a rectangular cross section here, this is the same rectangular cross section at this section as well. If it's a trapezoidal cross section here, it is the same trapezoidal cross section here as well, right? So if that is the case, then naturally v1 and v2 will be exactly equal, right? In that case, writing the Bernoulli equation for this scenario becomes very easy, right? It will just simplify very easily to z1, because y1 and y2 are the same, so they'll cancel out. v1 square by 2g, v2 square by 2g are also the same, so they'll also cancel out. So you are left with z1 equal to z2 plus hf, right? So I would encourage you to write the entire Bernoulli equation and then cancel out the terms. Then you'll end up with this very simple simplified expression for uniform flow. So Z1 equal to Z2 plus HF. So now I know, if I know the bed slope, let's say I denote the bed slope with the term S naught, right? So if I have S naught to be equal to the bed slope, then I can rewrite this expression simply as HF equal to Z1 minus Z2, which will be simply the bed slope S naught multiplied by the distance between these points, right? S naught times L. So that is HF equal to S naught times L. But as if you remember, we had already written an expression for HF. HF is simply F times L by 4R. Remember, this D, we have now replaced it with the hydraulic radius, 4R, because R was equal to D by DH by 4. So I've just replaced that with 4R over here, times V square by 2G, right? So now I have two expressions for HF. One is S naught times L, and the other is using the friction factor and using the knowledge that we've already gained from pipe flows. We are simply extending that to the open channel flow. Now I'm going to equate these two expressions. S naught times L must be equal to F times L by 4R into V square by 2G. I'll rearrange these terms and then I'll get an expression for V, right? And I get the expression that looks something like this. This is a very popular equation, which is called the Chezy's equation. So if I rearrange this, I'll get V equal to square root of 8G by small f. So f is the friction factor, times square root of R into S naught. Okay, this 8G by f, under root 8G by f, we replace it with the coefficient C, capital C, which is called the Chezy's coefficient. Okay, so this is the Chezy's equation, V equal to C under root R by R into S naught, right? Where C is the Chezy's coefficient. Okay, so this is very powerful equation, can help us solve a number of scenarios. Okay, so similar to this Chezy's equation, we also have another equation called the Manning's equation, okay, which is an extension of the Chezy's equation. In many experiments, it was observed that this Chezy's coefficient C is actually R to the power 1 by 6 divided by N, right? Where this N is what is called the Manning's roughness coefficient. Okay, so these are empirical equations. Okay, so you will have to so this understanding has come about uh, by doing a lot of experiments. Okay, so C equal to R to the power 1 by 6 by N. If I replace this C from the Chezy's equation with this expression R to the power 1 by 6 by N, where remember R is the hydraulic radius. If I do that, I get V equal to 1 by N R to the power 2 by 3 S naught power half. Okay, all I've done is I've replaced this C with R to the power 1 by 6 into N, and then multiplied it with square root of R and square root of S naught. So square root of R into R power 1 by 6 simplifies to R power 2 by 3. Okay, so this you can very easily verify. So this is the very famous Manning's equation. Okay, so this is a very powerful equation, and this equation in fact is something, again, that as a civil engineer, 10 years later, if somebody asks you Manning's equation, you should know what Manning's equation is. This is very popularly used, very widely applicable, right? So this is something that you should remember. Many years later, you should remember Manning's equation. So V is simply 1 by N R to the power 2 by 3 S naught power half, right? So we have these two expressions, Chezy's equation and Manning's equation, for estimating the velocity in a channel that is undergoing uniform flow, right? We can easily convert this to flow rate Q. Simply multiply both sides by A. You will get, for the Chezy's equation, you will get A into C into under root R S naught. This Chezy's coefficient C ranges typically between 30 and 90 meter per 1 by 2 per second. Okay, so this is a very mixed dimensions. So typically what we do is we don't even because it's mixed unit, which doesn't make any physical sense to us. We simply say Chezy's coefficient is 30 or Chezy's coefficient is 40. We don't even give the units. That's just by convention. Okay, but in reality, it does have some mixed unit, which of course I'm showing here. Similarly, with Manning's equation, I just multiplied this equation by A. I'll get Q equal to 1 by N A R to the power 2 by 3 S naught per half. This Manning's roughness coefficient N typically ranges in value from 0.01 to about 0.15. This again has mixed unit, meter power minus 1 by 3 times second. Okay, so it's a very mixed unit. Now these both of these equations are very powerful, as I said. So suppose if I give you the flow depth and the cross section details, right? If I give you the flow depth y and the cross section details, you can very easily obtain v and q, right? You just have to put in, and of course I have to give you s naught also. Sorry, I forgot to mention that. If I give you s naught, flow depth and cross section details, you can very easily obtain v and q, right? Using this equation. The other thing you could do, if I give you the flow rate or the velocity and the cross section details, then you can also obtain the flow depth using this equation, right? Assuming that you know S naught, right? If I give you Q and the cross section details and you know S naught, you can uh, obtain the flow depth from this, because A and R are functions of the flow depth, right? Okay. So now the interesting thing is that the flow depth at uniform flow, we refer to it with this terminology called normal depth, right? And typically we use the expression y naught to refer to it, right? Some textbooks will say yn, but I prefer to use y naught. Okay, why not? I can use whatever I want, right? So why not? So flow depth at uniform flow is called normal depth. Okay, all right. So what we'll do is very quickly we'll solve a couple of problems using this Chessy's equation and Manning's equation. Right. So first problem: a straight rectangular channel is 2 meters wide and 1 meter deep, and laid on a slope of 2 degrees. If the Chessy's coefficient is 60, see, I said although it has units, I'll simply refer to it as 60, okay, because the units is too cumbersome to carry it around, right? If the Chessy's coefficient is 60, estimate the uniform flow rate, right? So it's a very simple application of the equation. So we know that it's a rectangular channel, we know the width, and we know the depth of the flow. So y is 1 meter. The rectangular channel, typically we use capital B to refer to the bottom width of the channel, right? Capital B equal to 2 meters. So A is simply B times Y. It's a rectangle, right? So 2 times 1, so it's 2 meters square. The wetted perimeter P is 2, which is the bottom width, plus 2 times the side, the height of the flow in the channel, right? Because it's a rectangular channel, so you simply have to, the wetted perimeter is the length of the two sides of the rectangle plus the bottom of the rectangle. The top surface is exposed to the atmosphere, so that doesn't count in the wetted perimeter. So it's 2 plus 2 times 1, so that's 4 meters. So I know A and P, I can simply find out R. R is A by P, so that is 0.5 meters. Okay. S naught is given to you, it's tan of 2 degrees, right? That is the slope of the channel. So now you know everything. You know the Chessy's coefficient, you know R, you know S naught. You can simply solve for Q. Q equal to A times C times under root R S naught. You put in all these terms, you get 16 meter cube per second, right? Now the same problem, I can give it to you backwards, give you the flow rate, give you the that it's a rectangular channel with a depth with a width of 2 meters, and ask you to find the depth of the flow, right? So then in the same equation, everything will be known except y. It's one equation, one unknown. You can back calculate and find out y, right? So I can do it either way. If the flow rate is known, I can ask you to find the flow depth. If the flow depth is known, I can ask you to find the flow rate, right? So that's a very simple application. One more problem. An asphalt-lined trapezoidal channel with a Manning's roughness coefficient of 0.016, as shown, carries 9 cubic meters per second of water under uniform flow conditions when S naught equal to so and so 0.0015. What is the normal depth? Right? So it's a trapezoidal channel of the following. The bottom width is capital B equal to 2 meters. Side slopes are at an angle of 50 degrees with the horizontal. We are asked to find out what this y naught is, right? So in the trapezoidal cross section, there's one more parameter that we can introduce, which is called the top width, right? The top width of the channel cross section. So this top width T, you can very easily see it will be B plus 2 times this length, right? This length is because the channel is symmetric, you can estimate this T as B plus 2 times this length, right? Using geometry and this 50 degrees and so on, you can find out what that is. So that will be T equal to B plus 2 into y naught cotangent of 50 degrees. Okay, I'll leave the geometry to you. You can very easily figure that out. Similarly, A, which is the area of the cross section, will be half B plus T into y naught. Okay, I'm not going to explain all this. This is fairly straightforward. The area of a trapezium, So I input all these values, I get this expression over here. Similarly, the wetted perimeter will be B plus 2 y naught cosecant 50 degrees. So the wetted perimeter is this length plus this length plus this length. So it is B plus 2 y naught cosecant 50 degrees. This again, the geometry is all straightforward, so I'm not going to explain all of this to you. Okay. So then I input it into the equation Q equal to 1 by n a into r bar 2 by 3 s naught bar half. Right. That was the Manning's equation. So n is given to you 0.016. So 1 by n a into r power 2 by 3. So now remember, r is a by p. So a into r power 2 by 3, I rewrite it as a power 5 by 3 and p power 2 by 3. Right? I hope that's clear. Right? Maybe I'll just quickly just write it here. A into r to the power 2 by 3. Right? Since r is a by p, this becomes a power 5 by 3 divided by p power 2 by 3. Okay, so this is fairly straightforward. Okay, so that's what I've done over here. Okay, so I've simplified this. I'm just erasing this. All right. So everything in this equation is known except y naught. But the problem is it's not so easy to solve this equation. So if I set up the equation, I'll get something that looks like this: 2 y naught plus y naught square cotangent 50 degrees to the power 5 by 3 equal to 3.718 blah blah blah. Okay, so this is a fairly cumbersome equation to solve. It's not difficult to solve. You can very easily solve it, with Excel or something like that. But naturally, you need some kind of a iterative solution. The simplest thing would be to assume a value of y naught and evaluate the left hand side, evaluate the right hand side. If they are equal, then your guess is correct. If it is wrong, then keep revising your y naught until you get LHS equal to RHS. That's the easiest way of solving this kind of a problem. So if you do it iteratively, you will get y naught equal to 1.387 meters. So this is another example of using the uniform flow approximation to solve problems, right? In this case, I'm giving you the flow rate and asking you to find the flow depth. In the previous example, I gave you the flow depth and the cross-section details and asked you to find the flow rate. Right? So this is fairly straightforward. So the next thing we're going to do is we're going to move to this idea of most efficient cross-sections. Okay, for a given channel material, if you look at the Manning's equation, we easily see that Q is proportional to R power 2 by 3. Right? If I give you the channel material and the bed slope, then Q is proportional to R power 2 by 3. Right? So if I want to maximize the flow rate, I have to maximize R for a given channel material and a given bed slope. Okay, that I don't have control over. Right? So to maximize flow rate, I need to maximize R. How do I maximize R? For a given cross-section area A, R is maximum when P is minimum. When the wetted perimeter is minimum, right? Because R is A by P. If P is minimum, R is maximum, right? For a given cross-section area A, right? So I can use this expression to try to find out what is the most efficient cross-section, right? So imagine I have a trapezoidal cross-section just like I showed in the previous example. Bottom width is capital B, flow depth is y naught, and the side slope, instead of giving you theta, I'm giving you the side slope in this form, m is to 1, right? M horizontal, 1 vertical, right? If I give you this expression, then the wetted perimeter is simply B plus 2 y naught into square root of 1 plus m square, right? This you can obtain this very easily. So this is the wetted perimeter. So if I want to find the minimum wetted perimeter, I have to set dp by dy equal to 0. I'm not going to do the arithmetic. I'll leave it to you. You can very easily do this. And when you solve for this, you will find out that for minimum wetted perimeter, maximum R happens at at a flow depth. Sorry, maximum R is y naught by 2, right? So that is the cross section at which you will get the highest R and highest flow rate, right? For a given cross section area, if my hydraulic radius is half the flow depth, that will give me the maximum flow rate. Okay, so I want you to set this dp by dy to 0 and try to solve it. You just have to write this entire equation in terms of y naught. Okay, so then you'll be very easily able to do this. So you'll solve to find r equal to y naught by 2. That is the condition for a trapezoidal cross section of any side slope, right? I have not given any condition for this m. It can be any value of m as long as it is a trapezoidal cross section. The maximum flow rate happens when r, the hydraulic radius, is equal to y naught by 2. Now, if you think of a rectangular cross section as a limiting case of a trapezoidal cross section, that is m equal to 0, if you solve for that, you will find out that for a rectangular cross section, the maximum flow rate happens when the flow depth y naught is equal to b by 2. It is half the bottom width. Okay. So this is for a trapezoidal cross section. Remember, I have not placed any constraint on m. For any m, this is the maximum flow rate possible. At this r, maximum flow rate will happen. Okay. But if I want to find out the m at which maximum flow rate happens for a trapezoidal cross section, then you can apply the same principle. Instead of making y variable, you make m variable. So then you will have to set dp by dm equal to 0 and solve for it. If you do that, you will get m equal to 1 by root 3 or theta equal to 60 degrees, which means if the side angle is at 60 degrees, right, that is the angle at which you get best, uh, uh, highest flow rate q. Okay, which means it will give you the maximum r, which will give you the maximum q. Okay, so that is also this idea of the most efficient cross section. So suppose in a problem, I can give a problem in which I give the flow rate and then say, tell me what the flow depth should be such that the the cross section is most efficient. Then you will have to simply apply these principles and come up with the flow depth. Okay, all right. So the next topic we're going to talk about is this idea of what is called specific energy. Okay. Now, if you remember the total energy at any cross section, we have already defined it as H equal to, we didn't use the terminology H, I'm just going to use capital H. Capital H equal to y plus v square by 2g plus z. Okay, so this is the total energy. This we have seen even in the case of pipe flow, right? Okay, but now what we're going to do is we're going to define another uh, another term called specific energy, which will be denoted by the letter capital E as follows, right? So we are going to define this specific energy as E equal to y plus v square by 2g, which means I'm just ignoring this z term in the total energy. I get what is called specific energy, y plus v square by 2g, right? So if I have if I ignore the component of datum head, I get what is called specific energy, which is y plus v square by 2g, right? If I rewrite that in terms of q, I'll get y plus q square by 2g a square, right? So what I did was I took some random flow rate, and for a given cross section, I plotted how this E varies as a function of y, right? So you can clearly see in this second term, q square by 2g a square, this a is a function of y, right? For a given cross section, if I change my y, my area will change, right? So y is not only here, it is not only E is not only directly proportional to y. It looks like that, but it's actually, there is y in the denominator over here. So it's a very complex function. So it's a cubic function actually, right? So E equal to y plus q square by 2g a square, where this a is a function of y, right? So what I did was I took a given channel cross section, I specified some flow rate and tried to plot this E as a function of y for different values of y. Okay, and when I did that, I got this. Okay, so now this is I've done this deliberately. Although I said E is a function of y, I'm putting E on the x-axis and y on the y-axis. Okay, I'm putting it that way. This is what the curve looked like, right? I used a certain value of q, and I tried different values of y. Okay, I assumed the cross section was a trapezoidal or a rectangular cross section. You can do it for any cross section; it doesn't matter, right? As long as you know the relationship between a and y for that particular given cross section, you can very easily create this curve for a given flow rate. So I did that, and surprisingly, I find that this curve looks something like this. The energy uh, decreases up to a certain point, the specific energy of flow depth. As my flow depth decreases, the energy also decreases, and then at a certain point it reaches a minima, and then if I continue decreasing the flow depth, the specific energy increases. Okay, So this point of minima is what we call the critical flow depth. Okay, if you remember from earlier, we had defined critical flow as Froude number equal to 1, right? We'll come back to that, right? And this portion of this curve that is above this critical flow depth is called the subcritical flow regime. So these depths are subcritical flow depths, and these flow depths are supercritical flow depths. So this is above the critical flow depth is subcritical, below the subcritical flow depth is supercritical, right? So for a given flow rate, this minimum specific energy corresponds to critical flow depth, which means Froude number equal to 1. Okay, I'll prove this to you a little bit later, so please hang on. Okay, so this is very interesting. So this minimum specific energy happens at a single value of flow depth, right? And that depth is called the critical flow depth. For any other specific energy, right? So if I take any other specific energy and draw a straight line here, it will intersect the curve at 2 points, right? It will intersect the, for all other values of specific energy, there are 2 possible flow depths, right? Only at this minimum, this straight line intersects this curve at 1 point. At any other point, if I draw this curve, it will intersect the curve at 2 points. One will be at a subcritical flow depth, which is the Froude number less than 1, if you remember from our earlier slide. And the other will be the supercritical flow depth, where the Froude number is greater than 1. Okay. So I'll prove this to you a little bit in the next slide and the next couple of slides. Okay. So for a given Q, if I set dE by dy equal to 0, right? Because here, if you go back, you see E as a function of y, it reaches the minimum at this what we call the critical flow depth. I'll prove that to you a little bit, just in a few seconds. Okay, I'm going to set dE by dy equal to 0, right? So dE by dy is 1 minus q square by g a cube dA by dy, right? If you just go back to your expression for E is y plus q square by 2g a square. So if I'm differentiating this with respect to y, so dE by dy will be 1 minus q square by 2g a cube. Okay, let's just go here. Q square by g a cube into dA by dy, and this I'm setting to 0. Okay, so now I want to find out what this dA by dy is. Okay, so let us say I take any random cross section which has a top width of capital D. If I take an elemental flow depth of dy, right? The area of this elemental flow, elemental surface is simply dA, which is equal to T times dy, right? So I take some random cross section, right, which has some flow depth. At the top, I have the top width of capital T, right? So then I take a small elemental area at the surface of the channel of depth dy. So the area of this elemental area will be dA, which is equal to T times dy, right? It's fairly straightforward. We are assuming that this dy is so small that this is almost approximated as a rectangle, right? So I can very easily find out what dA by dy is. dA by dy is capital T, right? So I'll replace it over here. dA by dy, I'll replace it with capital T. So I'll get q square T by Ga cube equal to 1. Okay. So this is the condition at which the specific energy reaches the minimum. Okay, like we saw in the curve that we just saw previously. Okay, so what this means is for a given flow rate, critical flow corresponds to minimum specific energy. Okay, now I'm going to invert it and say, what if I keep the specific energy constant and vary the q, right? If q is variable and we set dq by dy equal to 0, we'll get something like this, right? E equal to y plus q square by 2g a square. I rewrite this as q equal to a into under root 2g e minus y, right? Right. So this I'm writing this entire expression in terms of the area and the specific energy and the flow depth, right? So let us set this dq by dy to 0. dq by dy will be under root 2g into e minus y multiplied by dA by dy, this term, minus, then I'm just applying chain rule, right? Ga divided by under root 2g e minus y equal to 0. Right now, in this equation, we know a few terms. What is dA by dy? We just saw that in the previous slide. dA by dy is t, right? And what is this under root 2g e minus y? Under root 2g e minus y, we see over here. That is equal to q by a, right? So I'll replace this under root 2g e minus y in both these terms with the expression q by a, which is simply this expression, right? So I'll get t dA by dy into q by a, this square root term, minus ga divided by q by a. So I get T into Q by A minus G A square by Q equal to 0. So if I rearrange this, I'll get Q square T by Ga cubed equal to 1. Right? This is identical to the critical flow condition that we got. In the previous slide, if you remember, we set dE by dy equal to 0 and we got this expression Q square T by Ga cubed equal to 1. Okay, this is very, very important. You need to memorize this. There's nothing else that you can do, right? Q square T by Ga cubed equal to 1, right? This was the condition for minimum specific energy for a given flow rate. Now I'm doing for a given specific energy, I'm finding out that I get the same condition Q square T by Ga cubed equal to 1 for a given specific energy. Critical flow condition is that condition at which I get the maximum flow rate, right? So how do you have to check that d square q by dy square is less than 0 and so on, right? So you have to do the second differentiative to find out if it's minima or maxima. But I'm going to tell you that it's maxima. I'll leave that to you. Okay, you do that as an exercise, right? So for a given specific energy, critical flow corresponds to the maximum discharge. Okay, so this is very, very important. So this critical flow, you can interpret it two ways. For a given flow rate, critical flow corresponds to minimum specific energy, right? For a given specific energy, critical flow corresponds to maximum discharge. Okay, so both these statements are true simultaneously. So you will have to understand this, right? So now the next thing I want to do is, I've spoken about critical flow, and I've not spoken at all about the Froude number, right? Remember the Froude number in the very initial few slides, I had defined this Froude number as V by under root Gy, right? This I said was, if this is equal to 1, I said it's critical flow. And if it's less than 1, it is subcritical. If it is more than 1, it is supercritical. And now in this slide, I'm showing Q square T by Ga cube. These two terms look completely different, right? I'm saying if this is equal to 1, it is critical flow is what I'm saying, right? If you look at the previous few slides. And then, but Froude number is V by under root Gy. What is the connection between Q square T by Ga cubed and V by under root Gy, right? The relationship is very simple, right? Q square T by Ga cube, I can simply rewrite it as Q square by A square becomes V square by G into A by T, right? V square by G into A by T, right? I'm taking this T to the denominator. Q square by A square becomes V square divided by G into A by T, right? So that is actually equal to Froude number square, right? So now you may say, hey, how is Froude number square equal to G into A by T? It is under root Gy, right? Now, the interesting thing is, for a rectangular cross section, A by T, what will A by T be? For a rectangular cross section, top width is the same as the bottom width, right? So A by B will be Y, right? So this is a short form that we use, V by under root Gy. This is only applicable for a rectangular cross section, right? Froude number equal to V by under root Gy is only applicable for rectangular cross section. To be more precise, in general, we have to write Froude number as V by under root G A by T. Okay. So now this, as you can see, is Froude number, and this Q square T by Ga cubed is simply this number square. Okay. So therefore, that is the relationship between Froude number and your expression V by under root Ga by T. Okay. Of course, I wrote it in short form as V by under root Gy, because in the initial slide, I didn't want to confuse you all too much. But this term and this term are exactly equivalent, right? Of course, this term I've now revised it to write it like this. For a rectangular cross section, you can still write it as Gy, under root Gy. But for a general cross section, it is more appropriate to write it as under root Ga by T. Okay. So I know this is a lot of material that we have covered. So I want you to very patiently watch this, and please come up and ask your questions tomorrow when we have our class. So this is the specific energy concept is very, very important. I want you to pay special attention to this to make sure you understand this very clear. Okay. So as usual, we are going to meet on Tuesdays and Fridays. We have the class tomorrow on Friday, April 23rd, is it, or 24th? Anyway. So yeah, we'll meet from 10:30 to 11:45 on Friday. You can email me, you can send me your questions by phone or WhatsApp. All right. So thank you very much. Let's meet on Friday.